Hey Braves, have you ever wondered where all the things and elements and atoms and things that make you came from? Would you believe me if I told you that everything that is inside of you now, not only did it used to be inside of a dinosaur or a saber-toothed tiger or some weird thing swimming around in the ocean, before it even got there, it came from the center of a star. You are made of star stuff. And as you found out in the last video you just watched, all of the elements heavier than hydrogen and helium essentially came from the core of stars or during a supernova explosion. Now, we all know, as we found out last week, the sun will only really make things up to about carbon. That's as big as the sun is, and it doesn't have enough gravitational pressure or energy to fuse anything beyond that. So the sun's going to stop at carbon. But if we had a bigger star, well, those will fuse things in their core all the way up to iron. Now that's where they stop, those big stars. They can't make anything beyond iron because in order to basically fuse iron any further, you have to put more energy in than you get out from the fusion. It just doesn't work. What is necessary to fuse things beyond iron, so all of those radioactive elements and gold and everything else, in order to get there, well, we need the high pressures and energies of a supernova explosion from one of those supermassive stars. So once a star explodes in a giant supernova, well, where does all that material go? It goes back out into a gas nebula, just like where this star originally started from, and one of those nebulas, those gas nebulas that eventually became a protostar and then a full-fledged star. Well, once a star goes supernova, there's generally enough material left behind that nebula that exists afterwards can, once again, gravitationally pull itself back together to create a new star. Now this is a really big cloud of gas, these nebulas, like much bigger than our solar system. So there's a whole bunch of material after these supernovas that can turn around and create not just another star, but another solar system. Now, in order to get the amount of heavier elements that we have here in our inner planets, Mercury, Venus, Earth, and Mars, in order to get those dense elements, we would have needed at least 2 stars to have gone supernova in our galactic neighborhood here, wherever we are on the Milky Way galaxy, to have enough material to create this stuff. So we are a 3rd generation solar system, and Sol is a 3rd generation star. Now, what that means, folks, is everything inside of you right now either came from the center of a star or during the death of a star. So you are made of star stuff, or stardust if you want to say it that way. Pretty awesome, right? Now, how did we get all of the planets after these 2 supernovas occurred? Well, much the same way a star forms during the protostar phase or the nebula phase, as all of that gas starts to pull itself, and gas and dust, I should say gas and dust, because we didn't just create gaseous elements, we created things like uranium and iron, and those aren't gas, right? So all of this gas and dust is floating around in this nebula. It starts to pull itself together, just like it did when, it was a star a long time ago. So it starts to pull itself together, and you have to think that the nebula isn't a perfectly even spread out amount of mass. So what that means is that more mass might be coming from over here and less mass might be coming from over here. And as they attract each other, they bounce into each other and they cause a spin over time. And because there might be more mass coming from one direction, it eliminates or pushes out or knocks out the gas and dust coming from the opposite direction until eventually the only stuff that's remaining is all going in the same direction. This is why all the planets revolve around the sun in the same orbital plane, so to speak. Now, just because I know it's hard to visualize this, go on ahead and watch this video here of a professor doing a much better job of demonstrating exactly this.
In reality, that big mass would feel the warping of space-time by the marble too, right? It would move a little bit, but we usually ignore that. The Earth makes the sun move a little bit, but it's so small you can ignore it. The moon makes the Earth kind of wobble around a point 3/4 of the way from the center of the Earth. We usually don't account for that when we're looking at satellite motion. Well, instead of just letting go of one, what if I give it a sideways push? Now it orbits. Now it's losing energy, which wouldn't happen in the solar system, right? Not noticeably. There's some perturbations from other planets and things, but this one does lose energy and spirals in. If I don't push it as hard, it will do an ellipse for a while anyway. And solar system, right? Why is everything going in the same direction? Well, the answer is it wasn't. Different directions. But there was a preferred direction. The disk it formed from had a slight preference one way versus another, and things going the opposite way got eliminated, and when it's all said and done, everything's going the same way. That works 90% of the time.
Is it like a toilet flushing? Southern hemisphere? Wow, can you do that again?
And so, it won't work then. And so I have slightly more in one hand than another, but I don't consciously do that. And you want to get them so they spread out a little when you throw it.
It's because they're colliding with each other that you...
The ones going the wrong way get eliminated, right? Now there also would have been, this is where this analogy breaks down. There's another dimension, right? But those things that were out of the plane also, that weren't near the preferred plane also got eliminated.
So, once all of that material starts essentially orbiting in the same direction, after the sun has started up and begun fusion and is now a sun or a star, the gas and dust will start to accumulate in this, what is called an accretion disk. Basically, an accretion disk is just the gas and dust all squeezed down into a frisbee that goes around the outside of the sun. Well, as that stuff starts to revolve around the sun, it starts to accumulate more and more stuff. Those balls of stuff continue to grow and grow until they're the size of asteroids, till they're the size of moons, until the size of planets. And once you get up to the planetary size, you will start to also get some leftover material starting to orbit that newly formed planet, and that's where your moons come from. Now, the animation on the screen there should do a fairly good job of kind of demonstrating this process. Now, the process itself takes millions of years to happen. It didn't happen overnight. So once the sun started, the rest of the planets hadn't formed yet. It took several million years for them to continue spinning around the sun over and over and over again until they all had enough mass and enough heat to form into the planets. Now, why, oh why, are the inner planets rocky and the outer planets gaseous? Well, that has to do with density. See, iron is much, much, much heavier per atom than, say, hydrogen or helium, right? It's a much denser material. So uranium is going to be less likely to be flung out to the outer edges of the solar system. And remember, the sun is burning with lots and lots of heat and putting off all sorts of solar winds and everything else. And those lighter elements are very affected by that, and that pushes them to the further reaches of the solar system. But those heavier, more dense elements aren't as impacted by those solar winds and other forces from the sun, so they stayed closer in the orbit. And that is why all of the inner planets are rocky and all the outer planets are the gaseous ones. All the gas ended up getting pushed to the outer edges of the solar system, and the dust kind of stayed closer to the sun. So we all know that in our solar system we have 8 or 9, depending on if you want to consider Pluto a planet. I still, in my heart, believe that Pluto is deserving of the planetary label, but, 8 or 9 planets. Well, how many moons do you think we have? See, the planets hold a lot of mass. They're really, really heavy, but they only have about 1% of the mass, and the sun actually has 99% of the stuff in the solar system. But what about the leftover stuff that made all those moons? How many moons do we have in our solar system? Would you believe me if I told you we have 200 moons in our solar system? Yeah, that's a lot of planetary bodies floating around other planets. So there's a lot of opportunities for we humans to expand out into our solar system and explore. Some of those moons actually could potentially hold life or be habitable for humans in the future once Elon Musk gets all the Mars stuff figured out and we have a space base. That'll be awesome, right? So if you look at all the moons in our solar system, who are the planets that have the most? I mean, 200 is a lot, and we only have 8 planets to hold all those moons. Well, the reigning king of mass in our solar system, the biggest planet, Jupiter, has 79 moons. But Jupiter doesn't have the most. In fact, the king title for most moons in the solar system goes to Saturn with 82 moons. Uranus and Neptune have 27 and 14 apiece, and even that tiny little Pluto has 4 tiny planetoid bodies. They're not quite the size of a normal moon, but they're moons floating around it. In fact, it has a sister moon that's almost the same size as it, and they kind of have a double orbital path where they're kind of wobbling around each other. So there was a lot of material left over to make all these planetary bodies. And that is how we were able to infer, not just the amount of heavy materials, but the amount of material overall to create all these rocky bodies. That's how we're able to infer that we are, in fact, probably a second or a third, most likely a third generation star system. So that is how we got all of our planets. That's how we got all the stuff that makes you, you. And that's pretty awesome, isn't it?